Okay, let's see. Elijah, can you hear me? All right, good. All righty. Actually, is this the 12th class today, or is it the 13th class? It might be the 13th class. I might have that wrong. I probably do. Yeah, it would have to be an odd number. We haven't missed anything yet. Okay. Then I just wanted to include that. And to kind of tie this in a little bit into our previous conversations, then this would be an output station here. So this is where you go in and define SAP 2000. I want internal element actions. You would do it at an output station. And so that's what the output station looks like. All right. So when there are no members, when there are no loads acting on the members, when there are only loads acting at the nodal locations, then this is how we can determine the internal forces. We can take that free body diagram, take the sum of the forces in the y direction, and we can solve for the shear at any location x, and it's equal to the shear at the first end of the member, v sub I. We can do the same thing and solve for the moment x at any location along the length, and the moment m at location x is equal to minus m sub I, the opposite of the moment at the first end, plus v sub I times x. And so based on that, we can draw shear force and bending moment diagrams. And so these two equations come from looking at a free body diagram of the part of this to the left, but we could also do the same thing for the part of that to the right of the section cut, or to the right of that output station. And you end up with the same results if everything is in equilibrium and all the constraints are satisfied. Okay, so for a first example problem, let's take a look at this beam. This is about as simple as it gets. It's a two-node model with one element. It is a cantilevered beam. So we have degree of freedom 1 and 2 at the left end. Degree of freedom 1 is a displacement. Degree of freedom 2 is a rotation. Degree of freedom 3 and 4 at the right end. Degree of freedom 3 is a displacement. Degree of freedom 4 is a rotation. So when we label our degrees of freedom like this, what we're going to find is that degrees of freedom 1 and 2 are restrained, and degrees of freedom 3 and 4 are free or unrestrained. So with only one element, we can write our member stiffness matrix like this. And so with E of 29,000 kips per square inch, I of 843 inches to the fourth, and our length L of 12 feet or 144 inches, there's the mistake you're going to make with respect to imperial units, is you're going to forget to convert the length from feet to inches, and that'll be a problem. We end up with this stiffness matrix. And since there's only one element in our model, this is both the element stiffness matrix and the global structure stiffness matrix. And so what we're going to do then is we're going to go directly to the solution process. No assembly here is required. No assembly required, right? It sounds like a tagline from a store. So we need the load matrix. We look at the loads that are acting on here. We have 10 kips acting at degree of freedom 3, but the 10 kip load is acting in the opposite direction from what we defined as a positive degree of freedom 3. So when we enter that into our load matrix, we have minus 10 there. So we can go through our solution process. One would be to just delete the rows and columns corresponding to degrees of freedom 1 and 2, but let's do it a little bit more sophisticatedly than that. And yes, sophisticatedly is a word. So what we're going to do is reorder and partition our matrix. So we have the free matrix corresponding to degrees of freedom 3 and 4. We have the restrained matrix corresponding to degrees of freedom 1 and 2. And then we also have K sub FR and K sub RF. Note that the loads P sub F correspond to degrees of freedom 3 and 4, and the loads on the restrained nodes, or loads on the restrained degrees of freedom, rather, are on degrees of freedom 1 and 2, and that's equal to 0 in this case. So what we can do is expand that. We can go through and solve for the inverse of the stiffness matrix, multiply as appropriate, and end up with our free degrees of freedom. So at degree of freedom 3, we end up with a displacement of 0.4071 inches downwards, and we end up with a rotation of 0.0042 radians. Counterclock, it's negative, so that's going to indicate clockwise rotation. You can kind of see right there an indication of the issue that I was talking about earlier with numerical precision. The resulting displacement corresponding the displacement's a hard term. The delta corresponding to degree of freedom 3 is 2 orders of magnitude larger than the rotation corresponding to degree of freedom 4. And so that issue gets exacerbated when you're working in millimeter units instead of inch units. So you have to be careful of that. All right, so those are the free degrees of freedom. If we bring back in our restrained degrees of freedom, we have displacements there of 0. So our total delta matrix is 0, 0, minus 0.4071, and minus 0, 0, 42. So what we can do is go back and solve for our reactions. I got my animations out of order. So when we solve for the reactions, we have R net is equal to K sub RF times delta F plus K sub RR times delta R. And then we can solve for the total reactions by accommodating the loads that are on the restrained nodes, P sub R. And in this case, P sub R is equal to 0, so it's a moot point. But when we get into an example later in this presentation, P sub R will not be equal to 0. So that's why I'm being a little anal retentive about including it here, even though it's 0. So then the next step is to look at the member end actions. So we solve for F sub I, the forces that are at the ends of member I. And I use the word force in 2 different contexts. One, it's obviously a force that pushes on something, but when we solve for the force matrix, it includes both forces and moments, right? So the first and the third element is going to be a true force in units of kips, and the second and the fourth element of that force matrix are going to be moments in units of kip inches in this case. So we have to be a little bit loose with our terminology, much like I'm calling it a delta matrix, but half of the items in the delta matrix are actually rotations. So we end up with our force matrix for the first element. The only element is we have 10 kips at the left end, 10 kips at the right end. We have a moment at the left end of 1,440 kip inches and a moment at the right end equal to 0. And from statics, and you'll find that satisfying, we know that if we have a free end of a member, the moment has to be equal to 0, and that's what our matrix analysis also found. All right, so what we want to do is solve for our internal member forces, our shear forces and bending moments. So if we take a look at our element with the end actions that are on it, we have 10 kips at the left, we have minus 10 kips at the right, 1,440 kip inches at the left. Then what we can do is say that V at any location X along the member is equal to 10 kips, and that gives us our shear force diagram. We can go a step further and say that the bending moment at any location X is equal to minus M sub I, minus 1,440 kip inches, plus the shear force at the left end times X. And so we end up with a bending moment diagram that looks like that. And then, so the trick is to come in and you close off these diagrams so that they look like the diagrams that you're used to sketching in by hand. And so that's a formality that you would handle at the end of that exercise. All right, so it's a relatively straightforward example, but it illustrates the process. So when we move along further into here, we'll make the problems just a little bit more complicated. So, like I said before, one of the nice things about these beam elements is that we don't have to worry about coordinating between local coordinate systems and global coordinate systems, because unless we're being mean to ourselves, unless we're masochistic, we align the beams parallel to the global x-axis. So in that case, the angle between the 2 coordinate systems is equal to 0, and we end up with the local matrix equal to the global matrix. So there's no reason to consider rotation at all. Now, when we get into problems that have more than one element, then we do have to consider assembly, but assembly is also a bit easier in this case than it is in the case of a truss or a frame when we ultimately get to frames. If we consider this example, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 degrees of freedom, and we have 1, 2, 3, 4 elements. So when we go to assemble the stiffness matrix here, what we'll do is we'll write 4 by 4 stiffness matrices, and when we assemble them, because the first element, let's call this element A, that has degrees of freedom 1, 2, 3, and 4 associated with it. If we go and look at the second one, B, it has degrees of freedom 3, 4, 5, and 6. So it's going to overlap like that with the element stiffness matrix for member A. When we do the same thing for member C, the first 2 degrees of freedom for member C are going to overlap with the third and the fourth degrees of freedom for member B. And then when we go and look at member D, the first 2 degrees of freedom for member D are going to overlap with the third and the fourth degrees of freedom for member C. And so when we go through our assembly process for a beam problem, it's very repeatable. And unless you were to number the elements in a very strange way, you always end up with the upper left 2 elements of a stiffness matrix overlapping with the lower right 4 elements from the member to the left. And so our assembly process is much simpler in this case than it is in the case of a truss, where you have almost arbitrary degrees of freedom at the ends of the member. So with those 2 observations made, let's go ahead and look at another example. And this is an example that I'm going to work a couple of different ways. The first way, I'll call it example number A, or letter A, is with the 10 kip load applied to node 2. And so we have 1, 2, 3 elements. We have 1, 2, 3, 4 nodes, and we have 2 applied loads. One load is truly a force. The other load is a moment, but they are applied loads nonetheless. So when we go in and formulate our solution to this problem, I'm going to number my degrees of freedom logically like this, moving from left to right, where all the odd number degrees of freedom are displacements, all the even number degrees of freedom are rotations. And so what that allows us to do is to develop our element stiffness matrices like this. So there's the element stiffness matrices A, B, and C already in global coordinates because our members are aligned parallel to the x-axis. And so when we go through and assemble this matrix, basically we're going to see an overlap between these 4 elements and these 4 elements here. And when we do the second part, I'm trying to change pen colors. We're going to see that these 4 elements here overlap with those 4 elements like that. And so basically you just add these together. You add this guy to this guy, for example, and it's easier to push with my finger, I guess. You add, say, this guy to this guy, and that gets you the assembled matrix. So on the next slide, slide 25, you see the assembled matrix. And so this corresponds to member A. These 16 elements correspond to member B, and then these 16 correspond to member C. Now, when we go in and we look at our loads on this, we have a 10 kip force applied corresponding to degree of freedom number 3, but it's in the opposite direction. So that'll be a negative 10 kips. We have an 80 kip inch moment applied corresponding to degree of freedom number 6, and it's acting in the same sense, so it will be a positive value. So when we go in and look at our load matrix, then the P matrix that I have here would look like that. And then our restrained degrees of freedom are going to be degrees of freedom 1, 5, and 7. And since we're not imposing any support settlements, all of those values are 0. So the solution process from here on out is basically mathematically identical to a truss problem. We partition the matrix. We reorder the degrees of freedom, putting the free degrees of freedom first, the restrained degrees of freedom second. Then we subdivide the matrix into its 4 submatrices: K sub FF, K sub RR, K sub FR, and K sub RF. And so we can go through the solution process that you're familiar with by now. We invert the free matrix, multiply by the appropriate loads, and we end up with our free displacements. And so here's the free displacements at degrees of freedom 2, 3, 4, 6, and 8. And what I'll do is bring in the complete displacement matrix that includes the restrained degrees of freedom as well. And this is nice because now I can use a VLOOKUP function to look up the displacements corresponding to the appropriate degree of freedom, or I can use an index and match function pair in order to solve for the same thing. And so what we do then is we solve for the reactions, and then we can go back and look at our member end actions. So we have for member A, for member B, and member C, we have these member end actions, F sub A, F sub B, and F sub C. So what we would do then is we will typically want to draw or sketch a shear force and bending moment diagram. So we go into our element formulation like this, and we know that F sub Y is equal to, V sub X is equal to V sub I, M sub X is equal to minus MI plus VX. And then we can go through and using these end actions, then we can sketch our member forces. And then, as a last step, what we would do is come in and basically just close these guys off like this, right? There's a line there. There's a line that comes up here. This is actually connecting here. This is connecting there. And I left the gaps there because it kind of correlates with the ends of the members that I have shown up there. But typically, we like our diagrams to be continuous. All right. Let's see. What I think I can do at this point is go ahead and show you the Excel sheet that goes along with that. And so one of the nice things about this is that you can, because the element, because the assembly process is rather repeatable, you can do the solution process for each one of these examples on a single page, and you don't have to break it up into multiple pages like we did with the truss examples. Excuse me. So yeah, here's the source code, if you will, behind that example problem. And you can see up here, there's kind of an illusion. It says without a hinge. What we'll do is we'll come back and look at this with a hinge in it later on. And so here's the 3 element stiffness matrices. And if I go here and do an F2 on that element there, you're seeing that I'm just adding the 3-3 element of the stiffness matrix for member A to the 1-1 element for the stiffness matrix for element B. And then I'm doing the same thing down here for, see that guy there. Yeah. And so it's a straightforward process once you've worked through a couple of example problems. So here's where I'm subdividing the matrix after it's reordered. Then we go ahead and invert the free stiffness matrix and just keep track of everything that's going on. So here are my displacements, right? So that's the result of multiplying the inverted stiffness matrix times the appropriate loads. And then here is the augmented matrix. So basically, I just put, the first 5 elements, I'm just copying. And then down here, what I have is a VLOOKUP function that puts them in order. So I find the first element, second element. Then when I come over here, now for these displacements, I have another VLOOKUP function where I can go through and find the appropriate displacement corresponding to the appropriate degree of freedom for that particular member. And then I stopped short. I suppose if you really had a lot of time on your hands, you could create an XY plot in Excel and plot the bending moment diagram, shear force diagram. But that's a little bit too much for me to spend my time on that. It's possible, but when we go back and look at the first example, then it's the same process. It's just only 1 element instead of 3 elements. All right, let me go back to PowerPoint then, and we'll move on unless you guys have a question. I didn't launch the chat window, so I don't see anything in the chat window though. Okay.
So we're only considering, we're not considering like axial forces because these are beam elements, right? Like when we're doing frame elements, that's when we'll include the 3rd degree of freedom in each node.
That's correct. Yeah. And so the way I chose to structure the presentation of this material was we start off simple with truss elements directly formulated in the global coordinate system. Then in the a subsequent lecture, we look at truss elements formulated in their local coordinate system and then transformed using pre and post multiplication. Now we go back and we add another complication, and that complication is that we're dealing with flexure and shear instead of axial force. So that makes things a little bit more complicated. And now we're about to include two more complicating factors. And the next one is what happens if we have a hinge in our beam. And so when we're dealing with trusses, we don't often worry about end releases in our matrix formulations. Yes, in visual analysis and in SAP 2000, when we model a truss, we have to include end releases there. But that's because every model in visual analysis and every model in SAP 2000 is a frame model. And in order to get the truss behavior out of that, we have to release the end moments of our beams. But with the truss analyses that we're doing in Excel, we formulated it directly as a truss element where there is no end moment in the member, and so we don't have to put any releases. So when we look at the beam element formulation, though, we have to accommodate pins from time to time. And if you go and look at SAP 2000 or visual analysis, you have to also consider axial releases or shear releases as well, or torsion releases too, if it's a three-dimensional frame. But in our beam element formulation, we're only going to consider hinges. So that's the one that's most commonly used. So I feel good about just keeping it to that. So there are a couple of different ways of doing this. If we're using what I call the direct stiffness method, then the simplest, the most straightforward approach is to use a different stiffness matrix for the beam element that has a release in it. So if you have, that's odd, if you have a release at the first end at the ith node, then you would expect that the moments that are associated with that are going to be equal to 0. So you zero out the row and the column of that stiffness matrix that correspond to the second degree of freedom, the released degree of freedom. Now note that the other elements of the stiffness matrix aren't the same. It's not as simple as just going in and substituting zeros into the stiffness matrix that we derived. In fact, if we were going to do this properly and completely, let me see what I've got coming up here. Yeah, what we would end up doing is we would go back and do a derivation of this. And what we would do is we would, yeah, the pen's not working now. Why would it work before and now it's not working? Oh, I had white as my ink color. Duh. Okay. Yeah. So we would do this where we have a node at the left end, then we have a pin, and then we have our member, and then we have a node at the right end. And over here, if we did the same thing, we would have a node, we would have our member, then we would have a pin, and then we would have our other node. So over here on the right, if we impose a unit displacement corresponding to the first degree of freedom, then that node moves up like that. This node stays here, but when we sketch in our deformed shape, it doesn't look like this, like it did the last time. Instead, what it's going to look like is this, right? Because this is free to rotate relative to the node. So even though the node doesn't turn, the end of the beam turns relative to that node. And then when we impose our second degree of freedom, we would rotate this element like that, right? That's the end node. But because there's a pin here, there's no associated displacement at all to the member. And that's why we end up with zeros here. Okay. And then we could do this, make the same argument over here. When we move this node upwards like that, the displaced shape that we would end up with would look like this. And when we rotate that node by 1 unit, 1 radian, because it's pinned, there wouldn't be any deformations to the member whatsoever. And then that gives us our fourth column of zeros in that case.
So in our previous example, those weren't pins. Those.
That's right.
Supports that looked like pins.
So let's go back to that layout. Where was it? Here we go. Yeah. So this is a pinned support at 1. So we're restraining degree of freedom 1, but that node is free to rotate at corresponding to degree of freedom 2. But that
Okay.
doesn't mean that it's an internal hinge. It's a pin support. So remember our difference between a release and a restraint. So it's a pin support, which is alluding to the restraints. But this particular example doesn't have any internal releases.
Gotcha.
Okay. All right. Now, so that's the most straightforward approach to including hinges, is to do that. There are other approaches as well, and if we get away from what I call the direct stiffness direct stiffness method, and go to a finite element formulation, then there are more sophisticated ways of handling these releases. And in fact, if we were to tear SAP 2000 apart, it probably uses a finite element formulation for the beam elements instead of a direct stiffness approach. And so when it derives the element stiffness matrices, it's probably using something like Lagrangian multipliers or something more sophisticated like that to handle the end releases. And that's why it can handle any kind of release and not just a moment release. So in order to illustrate this, I don't have it included in the PowerPoint, but I do have examples included in Excel where we can look at example 3B. So here's example 3A. Let me go up, scroll up here to the top and zoom in a little bit so you guys can see it better. Yep, there we go. So there's no hinges there. But what happens if I want to put a hinge in at that node number 2? So I can come in and I can put a release at the right end of member A. And when I do that, note that my stiffness matrix reflects that, right? So this stiffness matrix has different formulas in it than the stiffness matrix for elements B and C, right? The first element in the stiffness matrix for member A is 3EI over L cubed. And the first element of stiffness matrix B is 12EI over L cubed. And that's because member A has a release on it, but member B does not. So then the process is handled similarly from here on out. We go through and assemble the matrix the same way that we did in example 3A. We reorder and partition it, and we solve for our member end actions. And so one of the things that you'll find is that we don't have any end shears or any end moments for member A because of that pin. All of the load is carried by the beam to the right of node number 2. Now, when we look at this, we have the option of putting that release in at the right end of member A or at the left end of member B. And so example 3C has us putting in that release at the left end of member B instead. And so now when I look at the element stiffness matrices, note that the second row and second column of the stiffness matrix for element B are zeros. And that's because that is a different stiffness matrix because that element has a release in it. And so that works out just fine. We can go through the assembly process again. We can solve for the free degrees of freedom, and then we can ultimately solve for the end actions in the member. And you'll see between example 3B and 3C, we end up with exactly the same results. It doesn't make any difference once we get past the assembly stage. The global structure stiffness matrix is the same, regardless of whether you put the release in at the right end of member A or the left end of member B. Now, one thing that you can't do, I've been preaching this right along, is that you can't put a pin in on both sides of that node. So if we put a release in on the right end of member A and on the left end of member B, you can see here that I've got that reflected like this, right? So we've got two member stiffness matrices that are adjusted to reflect that release. When we go through and assemble our stiffness matrix, we have a zero element on the diagonal. And so that global structure stiffness matrix, even the reordered and partition, has a zero element on the diagonal. And so that means that free stiffness matrix is no longer positive definite. And that says that there's going to be an instability in the model. The structure that we're trying to model is unstable, is what that means. And in fact, if we go through and try and invert that free stiffness matrix, then Excel gives me that error. And that's expected, right? That's telling us that node number 2 is free to spin about an axis parallel to the z-axis for that. And so I did this as an academic example to show you mathematically what's happening in Excel and visual analysis when you've over-released a node and you get that error. All right, so that's how you deal with releases. You have 3 different stiffness matrices for beam elements. The default is when there aren't any releases. You have a second one when you have a release at the first end of an element. You have the third one when you have a release at the second end of an element. So that's basically just a series of if statements if you're programming this, or you just type in different equations into the cells in Excel when you formulate the element stiffness matrices. All right, let's go back to PowerPoint now. Another problem, another issue that we need to tackle is that when we deal with beam elements, we need to apply loads to members, right? We can't always apply loads to nodes. If we're handling concentrated loads, we can always put a node at the location of the load. But if we deal with distributed loads, and we want to, and we should, then we can't just put a series of nodes there. I think I have an example problem. I don't know if it's in here. I won't take the time to show it, but I actually took the beam up and I broke it up into a series of elements that were each 12 inches long. And then you can put a series of point loads on that represent a uniformly distributed load. And that works, but boy, is it cumbersome, and it's just not an elegant solution at all. So what we need to do is we need to calculate equivalent end actions to put on our beam. This wasn't a problem in trusses, right? Because a traditional formal truss formulation, we never have any loads applied along the length of the member. If it's a true truss problem, all of the loads are applied at the joints by definition. So it wasn't a problem in trusses at all. So let's consider a fixed beam like this. And if we have a fixed beam with a point load at the middle of the beam, then we could solve for the reactions. Yes, this is indeterminate, so we'd have to be a little bit more sophisticated than just using statics, but we could do this. We could solve for these reactions. And what you would see is that we have end moments equal to PL over 8, and we have end shears equal to P over 2 for that particular case. Now, what we're going to do is we're going to take these fixed end actions, the beam reactions for a fixed beam, and we're going to define something that is called equivalent end actions. And so if we put a point load on an element or on a beam at midspan or in between the two nodes, then we could represent that point load with a series of equivalent actions acting at the nodes that are adjacent to the loaded member, the loaded element. So in this case, let me go to the next slide. We have an element with a point load acting at midspan, and we can't handle that in our matrix formulation. There's no way of putting a member load into our matrix formulation because the degrees of freedom and the loads have to correspond to each other. But what we can do is we can come up with a set of equivalent actions that act at the nodes that the member is attached to that represent that load. So if we have a member force P acting at midspan, the way that we represent that in our matrix formulation is to put 2 end moments, PL over 8, at the 2 nodes adjacent, and we have 2 end shears that we apply at those nodes, P over 2. Now, we call them end actions because 2 of them are forces and 2 of them are moments. So action is a non-binary term when we refer to forces and moments. I appreciate the smile, Carson. Thank you. So that's why we call them equivalent end actions. You call them fixed end forces, fixed end actions, equivalent end actions, equivalent moments. But you have to be careful, though, because let me go back a slide. If you look at the fixed end actions and the equivalent end actions, they're basically opposite of each other in sense, right? The magnitudes are the same, but the moments are acting in the opposite directions. The forces are acting in the opposite directions. So when you go to a table and look up fixed end actions, you're actually looking up the reactions to a fixed beam. But when you go and do a matrix formulation and you enter the loads, you don't want the fixed end actions. You want the equivalent end actions instead. And then to make life a little bit more complicated, the way that they're presented here doesn't necessarily correlate with what we've defined as positive degrees of freedom. So we have our degree of freedom definition shown at the top, but some of these moments are acting in the opposite direction, right? If we go down here and look at this guy, that's acting in the opposite sense of that moment there, right? And there are two forces are acting in the opposite direction of that. So typically what we'll do is we'll write these equivalent end actions in a very goofy way. We'll write them like this with a load acting upwards, right? We don't often put the load acting upwards on the beam because most of the loads are due to gravity and they always act down. But it makes sense using, if we bear in mind our degree of freedom definitions to define our equivalent end actions like this. That way we can just enter them directly into our spreadsheet without having to think as much. You don't have to think, all right, am I looking at fixed end actions or am I looking at equivalent end actions? Is this moment really positive? Does it correlate with the moment that I have defined for my degree? And so when we present our equivalent end actions, we'll often present them the way that I have shown here at the bottom. And so two of the cases that we use most often are shown here, a point load at the center of the beam, a uniformly distributed load acting along the length of the beam. And so those are equivalent end actions that you'll see quite a bit. Those are the ones that I'll use straight off. But that's certainly not a full suite of equivalent end actions. You can have a whole lot more than just that. What if the load is off center a little bit, right? What if you have more than one load acting at the same time? And so I'm not going to present all of those cases to you. You can go to different resources for that. And one of the resources that I use quite often is the AISC Steel Construction Manual. If you go to the end of chapter 3, the end of the beam section, then there are a lot of different formulations for these beams presented. So you just have to be sure you're looking at the right case. Fixed on the left, but on the right, you're looking at cantilever beams instead. So you have to be careful of that. Couple more places you could look. I posted this on the Canvas site for your class before class today, and it's been there as a resource as well. This is something I found years ago when I went out and searched for fixed end moments or equivalent end actions. There was a nice handout that was posted on a website at Purdue, so I refer to it as the Purdue handout. If I had all the time in the world or more graduate students, I would have them rewrite this so it looks nice, and then I would present it as my own without, but no. So you have this available as a separate PDF. And so look at all the different cases that are presented there. The first one up here, let me get back to red ink so it stands out a little bit better. The first one up here is, a center point load. So that's PL over 8, PL over 8. What it doesn't show are the end forces. So you would have to solve for those yourself. So it's going to be P over 2 and P over 2. The second case is with the load off center, and it gives you the fixed end moments, FEM, for the end AB. So that's the A end of member AB. And then the second one on the right is FEM BA. So that's the B end of member AB. And so you have those as PB squared A over L squared and PA squared B over L squared. And again, you would have to use statics with those two end moments to solve for the forces that are associated with that as well. And you can go down here. Here's 2 equally spaced loads, 3 equally spaced loads. Here's when you have a uniform load acting over half of the beam. Here's a triangular loading for case of snow acting on a structure. Maybe you have a snowdrift loading or maybe a hydrostatic loading of some sort. And then this last one is particularly interesting. What happens if we have a unit displacement for one of our supported degrees of freedom, one of our restrained degrees of freedom? You can actually develop a set of end loads on the member that are reflective of that support settlement. I don't necessarily like the use of this approach, but it does work. I like to instead impose a support displacement and call it delta sub R instead, and then let the matrix operations shake out what the end actions for that member would be. And, the next thing you could look at here is that we have one column here where both ends of the member are fixed, but the second column over here is where we have only one end of the member fixed. So we have a fixed support at A, but support at B is pinned. And so the reason for that is that if you have an element with a release in it, the equivalent end actions for that element also have to be modified to reflect the fact that there's a pin in there. So if you had an internal release at the right end of the element, then these are the fixed end moments that you could use to calculate the equivalent end actions. If you had a case where the internal release was at the left end of the element instead of the right end of the element, then you would have to hold this up to a light and use the mirror image of it in order to solve for those values. But you have all of the quantities there that you would need in order to solve for those. The key takeaway from that last comment is that if you have a member or an element in your matrix formulation that has a release in it, the equivalent end actions for that element are different than they would be without that release. So the column to the left is what you would use without the release. The column to the right is what you would use for one of the two cases where you do have a release. And then for whatever reason, that handout from Purdue has some other ones that are included in it as well. The third resource that you have available to you is the in the back, I think it's inside the back cover of the Casamali structural analysis textbook. And here we have cases that are somewhat redundant with the Purdue handout, but there's a couple of cases in here that are different. For example, case number 2, you have a bending moment applied mid-length to the member. Now, I don't know where this would ever come into play, but I suppose that it could. And if you had a member loading that was a concentrated moment, then you can reflect that with these equivalent end actions. Now, note that it says these are equations for fixed end moments. So when you go in and calculate equivalent end actions from those, you have to first take the opposite of these. Then you have to correlate them with the degrees of freedom. And that's a great opportunity twice to screw up signs on these problems. And I know this because that's exactly what I do. Every time if I'm doing one of these problems, there's probably about a 1 in 4 chance that I'm going to screw up the sign on one of the equivalent end actions when I go through it. And then over here on the right, here you have a triangular shaped or trapezoidal shaped loading that's acting over part of the length of the member. So this equation here will handle just about any distributed load, but judging by Joe's face, yeah, that's not an equation you want to program into Excel, because when you try to do it, you're going to have to do it 5 times to get it right once. And then down here at the bottom, here's a distributed load acting along the length of the member. So it's an axial force, which is kind of moot in the context of a beam presentation, but this is ultimately a precursor to a frame formulation. So that will be useful. And then here we have a torsional moment. So if you have torsion acting on the member, you can solve for the fixed end moments due to that. All right, now let me take a drink here. One other complication that we have when we have member loadings on our matrix formulation is that the determination of the internal member forces after we've gone through the solution process is also more complicated. So in this case, this is basically the same approach that I was using earlier in the presentation when we solved for the internal member actions, right? We started off using this slide, but note that this thing down at the bottom doesn't have any member forces acting on it. So when we go and solve for the internal shear force V sub x and the internal bending moment M sub x, we have to account for loads that are acting directly on the members that we're working with. And so if we go in and reformulate that, then the shear at any point x is equal to the shear at the left end minus the distributed load times x minus the sum of p sub k. And I've written it like that, where you can have multiple forces p. So the kth load p, it could be the first load, the second load, the third load, where k is the load number. And so you could have any number of loads that are acting on the member. If you solve for the bending moment at any point x along the length of the member, it's equal to minus m sub I minus 1/2 wx squared minus the sum of pk times quantity x minus x sub k plus v sub x. And so solving for the internal shears and moments is more complicated, but it's not something that we can't handle, especially if you're endeavoring to write a spreadsheet or a program that's going to do matrix analysis of structures, and you're already a glutton for punishment. And so this isn't that big of a deal. It's tedious, but it's not terribly challenging.
Looking at this slide here, the right half makes sense. Intuitively, the two bending moments, the one on the right and the one on the left, are acting in opposite directions. But the one on the left, where they're acting in the same direction, makes less sense.
where you have M sub, whoops, I knew that was going to happen. Let me go back here, where you have M sub I acting counterclockwise and M sub X acting counterclockwise.
Yeah.
So the reason that I did that is that there are two different sign conventions that are used for M sub I and M sub X. I'll say this slowly. Hopefully I'll say it right the first time. M sub I and M sub J both use the sign convention that they're positive if they are counterclockwise. And that's because those are moments at nodes. M sub X is an internal bending moment. And yes, it's a moment, and a moment is a moment. But an internal bending moment, we use a slightly different sign convention. And the sign convention for an internal bending moment is that it's positive if it creates compression on the top fiber. So even though this bending moment is counterclockwise and this bending moment is clockwise, they're both positive.
Yes.
But that only works when you're drawing them in on the free body diagram. When you go in and take the sum of the moments, then you apply the sign convention like this, where that's positive X, that's positive Y, and that is a positive rotation. So when you're using statics, you only have one global sign convention, but when you're drawing them in on the free body diagram, we use the other definition for internal forces, right? And the same thing could be said for the shear force, right? This is a positive shear, but so is that. But when you go in and take the sum of the forces in the Y direction, when we account for this guy, it's negative, but when we account for that guy, it's positive. It's confusing. It really can be. It's more confusing when you explain it to sophomores for the first time when they're sketching shear force and bending moment diagram. And it takes a long time to convince them that it actually works. You guys were all there. I remember that. I was sitting in, I think it was the 8th floor of Benedum Hall in the University of Pittsburgh, and a guy named Mortuza Torquemani was teaching me. We used to call him Torque Monster because it was such a horrible class. I'm sure you have colorful names for me too, and I'm also sure I'm better off not knowing what they are. All right, moving on. So here we go back and look at that same beam, except now when I go through my formulation, I'm going to remove the node that was under the 10 kip load, right? So I used the first, 4 ways that I did this problem. I had 4 nodes. So now I'm going to take away one of those nodes. So in essence, what I do is I take that 10 kip load that was up to this point a nodal load, and I make it a member load instead. And so when we go through the formulation here, this is going to be my definition for the degrees of freedom. So I only have 6 degrees of freedom now instead of 8. And I can go through and write my element stiffness matrices for element A and B. But the one difference is that now I need to keep track of equivalent end actions. So P sub E are my equivalent end actions for each element. So I have a P sub E for member A, and I have a P sub E for member B. Now, P sub E for member A is going to be non-zero because I have a member load on member A, an element load on member A, but member B doesn't have any element load, so it's going to be 0. And so how did I get to those values of -5, -180, -5, and +180? Well, what I did is this, and I recognize that the handout that I gave you guys is a little different. In between the time that I posted it in class, I went back and I redrew this stuff in Visio. I've been working at improving these. Each year I'll go through and take a half a dozen slides, and I'll take my hand sketches and I'll redraw them, but it's tedious and it's not something that I get a whole lot of accolades for. So I just do it when I've got nothing better to do or when I don't feel like doing anything else. Anyways, this 10 kip force up here, the green loads or the green actions that are shown on the second version below are equivalent. So those green actions are equivalent end actions for that 10 kip force. And so when we go here, this is basically, maybe I should use green. That would require me to know how to do that. That just doesn't work. There we go. So this is basically PL over 2. So 10, no, it's not. It's P over 2. So that's P over 2. So that's equal to 10 kips over 2. This guy is also equal to P over 2. So 10 kips over 2. This guy here and this guy here each have the magnitude of PL squared over 8. So that's going to be equal to 10 kips times, you don't want to write in 12 feet, it's actually 144 inches squared divided by 8, and that gives you 180 kip inches. And so that's how we determine the magnitudes of those. And so when you go in and look at them like this is actually going to be -5 kips because it's acting opposite to what is positive for that degree of freedom. This is actually going to be -180 kip inches because it's acting opposite to what is positive. Remember, we had a positive degree of freedom like that. Positive degree of freedom here is 3 and then 4. And so this is going to be a -5 kips again, and this is going to be, it's acting in the same direction, so this is going to be a positive 180. And so that's how we get to the equivalent end actions that are shown here. Okay, so the process is tedious, it's confusing the first couple of times you do it, but if you're methodical about it, then you can get the right answer time and time again. And then so we assemble our stiffness matrix 6 by 6. We reorder. So there's member A, member B. Then we reorder, subdivide, and I'm sorry, we've got two different. So we have nodal loads here, and then we have our equivalent end actions here. We actually have to add those together to get our total loads on the member, right? This was the applied nodal action of 80 kip inches. Then we can go through and we can subdivide and partition the matrix, invert the stiffness matrix, solve for our free degrees of freedom. We can repopulate for the restrained degrees of freedom, solve for the reactions, and then we can go back and solve for our member forces. Now, our member forces, we have one more step now because we have the possibility of having equivalent end actions. These are the values that we get out of our matrix operations. So we take the stiffness matrix multiplied by our displacement matrix, and that is equal to this guy here, F sub I net, where I is either for member A or for member B. But then we have to subtract out the equivalent end actions in order to get to the final, or what I call the gross end actions. And the rationale is this. When we come in and represent our member loads, we create these fictitious loads at these nodes in order to represent that 10 kip member force. And so we've added in 4 fictitious forces. They're not really there. They're just there representing that member load of 10 kips. So after we do the matrix analysis, we have to take them back out, right? We added them in as a temporary substitute to get a member force. And then before we calculate, after we do our matrix operations, but before we calculate internal shear forces and bending moments, we have to take them back out. So when we go back and look at that formulation, here it is. That's why we subtract out the equivalent end actions for each one of the members. And then the last couple of slides that I'm not particularly proud of is where I've gone through and done some hand calculations and shown you how they all work out for each of those members. And so next year, in between 11 and 12:30, I'll probably redraw those. And then there's your final shear force and bending moment diagram. So the process is complicated, but it's not terrible. And so what we'll do then is after you guys submit homework number 4 on Friday, I'll post the next homework number 5. And what it's going to consist of is the same beams that you're modeling right now in visual analysis and SAP 2000. We'll ask you to do a matrix formulation for those beams. And we'll make it simpler. We won't put a moving load on it or anything like that. But we'll ask you to do some matrix formulations for that. And I think that what I've typically done in the past is I've gone ahead and posted this spreadsheet here, even though it has kind of the answer. It'll at least give you enough to go by, and you still have to do a lot of work to get from here to the answer for that homework. So, all right, I'm out of time. Any questions before we wrap up? All right. Otherwise, I'll hang around for a couple minutes if you have an individual question you'd like to ask. I have office hours tomorrow between 1 and 2:30, and then we're back in class together on Thursday at 12:30. And what we'll do on Thursday, I'll address questions again about either the homework number 4 or about this stuff if you start tinkering with it. And then we'll dive in and we'll do some more work with things in SAP 2000. All right. Well, call that a day then.